Okay, thank you everyone. So thank you so much for coming. So I'm going to give a brief discussion on the research that I do here at the university, and then specifically how that connects with the proposed work for this project. So let me change here. So just a brief introduction. So this is a picture with my current lab. So I work on studying system dynamics, so pretty much using operations research. I have a mixed background from physics, operations research, and civil engineering. I'm a professor in industrial and systems engineering. I'm also an affiliate faculty with data science analytics. I'm a faculty fellow of an institute as well, the Data Institute for Societal Challenges. And what I do is using these type of analytical tools to model and optimize cyber physical social systems and their performance. So meaning systems that have some information component attached to it, some physical components, and humans taking decisions there. Of course, many of these types of systems are highly interdependent, so I consider the interdependencies that exist there, and also decentralization and distribution, so multiple entities taking decisions over the same type of system. And here some collaborations that I have had for the different projects. So I work a lot on infrastructure and also supply chain networks. So I work with transportation centers here, the Latin America Sustainability Initiative, and different schools and institutes as well. So let's talk about critical infrastructure and why I work on this, and also supply chains. So I work on this because it's critical to maintain the supply chains and infrastructure, so that the economy is working well. We have access to food, water, energy, and this is critical specifically now we're talking about defense or military functions and defense-related operations. So society depends on the supply chains and the infrastructure that we have for normal operation, not just so that we have access to the different utilities, but also for safety and well-being. Whenever we have normal operations of those, then we have economic loss, health issues, and for this in particular, security issues. So when we look now at the infrastructure security and how that affects resilience, there are different problems that we need to be addressing. So one is how fast these systems are growing in time, and this growth could be in space, it could be in demand and the technology. So there's a lot of adaptation coming on, for example, with AI now being so pervasive everywhere, and the different interdependencies that exist between these systems. Of course, the decentralization that exists in this. So how do we model, how do we operate and control these type of systems and the decision making that occurs here? And of course, we have multiple scales. So we could be taking decisions at a local scale, but they may have effect not just locally, but also regionally or even global. So it is important to acknowledge it. The same with the time. We may be taking decisions in days or months, but they may propagate throughout longer periods. So it is important to understand those multiple scales. And there are different hazards. Of course, here the main focus is on the natural hazards, but there are others that could be related to security, the direct attacks, like cybersecurity, etc. So looking at multiple hazards simultaneously is also important. And this type of interdependencies, modeling this in infrastructure, is prevalent. So the government is very interested in this, and different agencies, not just the DoD or DoW, but NIST and National Science Foundation, among others. So let me give you some examples of the type of things that we're doing, and I'll finish with specifically what I envision to do for this project. So on one end, so here, by the way, I'm putting different types of hazards, natural hazards, that different communities are subjected to, and the type of analysis that we have been doing to address those. So, for example, here we studied Joplin. This is we studied tornadoes here, and what we wanted to study is, given certain budget that you have available, to take decisions with regards to for investments for retrofitting or restoration. Here, the idea was to study what is the optimal distribution of those resources, to know how much should be invested for pre-event versus how much should be invested for post-event actions. Not only that, but here in the models that we develop, we were looking at specifically which type of strategy we should be using where. So we were looking at individual structures in the city of Joplin. So we have the list of pretty much all the residential buildings and also commercial buildings, and knowing the different type of structures that they have. So in this case, because we're looking at tornadoes, we studied specifically roofing patterns and different types of roofs and how they could be affected by different tornadoes of different intensities and paths. So we are looking at establishing what would be a very worst potential tornado. So finding the worst path of a tornado given certain characteristics, to in order to reduce, so for us, in order to reduce the maximum worst case effect. So in other words, protecting the community against the worst case like potential effect. And we compare this with other approaches, and we show how useful this is, like potentially how much money and lives this could be saving. So again, just to summarize this part, is an optimization framework that helps us decide where to invest, where to take decisions on what strategies to implement, specifically looking at the type of hazards that we have, their likelihood as well. We could be looking also multi-layer. So this is another type of natural hazard, but for earthquakes. So here we were looking at three types of infrastructure. So water, gas, and power, and the interconnection between them. And considering the interdependencies also that exist here, we determine right after an earthquake what would be the optimal strategy for recovery, knowing what to restore when. So determining what components specifically of each type of network should be recovered when, so that the functionality of those combined systems recover as fast as possible. We also looked at also in the Memphis area, if there was to be an earthquake, some sort of disaster associated with an earthquake, that could also disrupt transportation networks. So even though decisions that you may take locally, they may affect the transportation in the entire country. So it's really, so that would affect people and also supply chains. So we looked into that also for the different scales here geographically. And here, something that we were doing, of course, in this type of problems is the scalability and adaptability. So this is also something that we could explore, and is that these type of problems tend to be very complex. So something that we could do, and we have explored very successfully, is to use purely data-driven system identification. So taking snapshots of what has happened in the past, to embed that into a model that would determine the key dynamics, the key dynamic modes of the system, then to predict behaviors of those systems associated with different actions that you may be taking. So in other words, to be able to do optimization without having to run these NP-hard models. And as we can see here, so like the predicted results versus the optimal versions, they're very similar, the same here. So the blue means that the decisions that you would take with one approach are almost identical or very close to the decisions that you would take if you were running the full optimization model. So this is quite useful. And we wanted to test here, so this is just a quick note here on the power of this type of data-driven system identification. So we wanted to test really how complex could these systems be for these type of models. So here to that test, we took the Standard & Poor's, something that we have zero knowledge about the dynamics, and it's the stock market. So we took different companies, we looked at the pricing, and we perform analysis with these data-driven models to forecasting of the behaviors, the dynamic behavior of that. And the errors are within 10% in general. So it is very good, and is able to replicate the key dynamics. And we can also discover interdependencies between the different components in that type of system. And we can extrapolate that for infrastructure. So it's really like understanding what components may depend on each other, even if you don't know physically those connections. But through the data, we can observe actually that there are some components that are critical and you should prioritize before others. And we observe also, even with the predictions here, how this dynamic mode decomposition approach work better than state-of-the-art type of models or gold standard type of models for predictive power. Everything with the goal of being able to determine the behavior of or the performance of these systems to take optimal actions. Now let me specifically focus on flooding. So going back to the optimization, which is specifically what we propose for this work. So for example, in this case, we looked at hierarchical decision levels, which I think would be very relevant here. So this we studied Lumberton, but the mathematical models can be translated to different locations as long as we have the same type of parameters. So here, what we have is different intensity. Let's say we have simulated different types of floodings in the region here in Lumberton. And for those, so we know for different water levels, we know the probabilities. And using that information and also knowing the different structures, like knowing their locations, we can determine which structure should be prioritized and what type of action should be taken to reduce the overall effect, negative effect of those disruptive events. Now, so for example, here the decisions could be elevating the floor of the building so that the water causes little to no damage in the buildings, specifically due to water levels growing. Here, not only we looked at that, but we also looked at hierarchical decisions in the sense that we assume that there's another entity taking decisions, perhaps putting barriers. Like here in this case, we studied the implementation of a levee around the city, and we could observe how the levee would help. So, for example, here, this is, let me point here with the laser. Okay, so let me do this. So for example, if you look at this region right here before the levee, so it was significantly affected. So you would have to invest heavily in those buildings to raise them. But if you build a levee, then you would see that almost no building would be affected. However, thanks to this type of analysis, we can observe also that other parts of the city that before were not affected, for example, in these parts and these around this part that were almost not affected, now will significantly be affected by putting a levee. So we can study here, if you're doing community level decisions, that's going to affect now more local aspects. So that's a hierarchical aspect here, in that you may have perhaps someone taking decisions that may affect everyone, and how the others would have to adapt to that, both in an optimal way. Assuming here, of course, that the first decision maker is trying to help the community, so but they may not be aware of these detrimental effects. Like in this case, they would have been thinking about what was affected before, but they may not have been aware of what they could be affecting negatively if they were to implement those decisions. So this is how hierarchical decision making. Let me change here. Something that, how do we lead this?
Are you getting close? We'll need to wrap up fairly soon so we can get Nisha on a
Yes, I have only 2 more slides. Yes.
Great, perfect. Thank you.
Yes. So this is just to mention fairness. So you may want to invest in one building or one structure versus the other. Just looking at cost, but maybe the way you're investing may be creating some differences in between the people. And so, for example, you have socioeconomic dimensions or other aspects. You may want to also include fairness and look at the multiple objectives simultaneously to see a trade-off. So here, for example, we're showing that you may just suffer a little bit in the economic loss, but gaining a lot in the fairness indices that you could be using. And then the last slide that I want to show you precisely for this is that you could be looking at multiple objectives simultaneously. This is what we want to have. So you could be looking at, for example, some objective that prioritizes economic aspects, some that prioritizes, let's say, repair time, and then you could build a Pareto frontier of non-dominated solutions so that this would show the trade-offs that exist for the decisions that you were planning. That's it. Thank you so much.